Hello everyone. Today I'm going to present you the proposed preset framework, which is short for Privacy-preserving Cloud-assisted quality improvement service in healthcare. It is part of my summer job. My project mentor is Dr. Shao Wang, and this is a joint work with Dr. Norman Muhammad, who is from McGill University, and Dr. Xiao Jiang from University of California, San Diego. Here is the outline of today's presentation. First, let's introduce the motivation. Suppose a few neighboring hospitals in a county may want to aggregate their local private medical data to perform some meaningful scientific discovery to improve the healthcare. However, due to the privacy concerns or institutional regulation, hospitals may not be able to exchange the data with others. Existing dissemination methods such as differential privacy just protect the sensitive medical data by introducing noise on the raw data, but it also degrades data utility. In contrast, the proposed framework tries to preserve the accuracy of results without introducing additional noise, and we resort to the combination of set encryption methods to achieve this goal. The following is the basic cryptographic primitive. The proposed framework is mainly based on two basic cryptographic primitives as shown in this slide. They are Homomorphic Encryption and Garbled Circuit. I will walk you through the detail of each primitive in the following few slides. Before introducing Homomorphic Encryption, let's first take a look at the traditional encryption method, where the data privacy is protected by data encryption during the storage and transferring. Here, for any further data analysis, one must first decrypt the data, then apply certain operations over the decrypted data. Finally, one can obtain the answer. The major privacy risk in this traditional method comes from the requirement of decryption before performing any additional operations. In contrast, in the homomorphic encryption, one can perform certain operations directly on the encrypted data, and the decrypt operation is only required when one wants to obtain the final results. Therefore, we can minimize the data privacy risk during the all life cycle of data processing. Despite this advantage of homomorphic encryption, it's worth mentioning that homomorphic encryption only supports limited operations such as the addition or multiplication with a high complexity overhead. And next, let's introduce the other cryptographic primitive, the Garbled Circuit. First, let's introduce the traditional circuit as shown in this slide, which can evaluate the function fxy by taking one input x from Alice and another input y from Bob. However, the privacy inputs cannot be guaranteed in this circuit due to the lack of protection. Then, its counterpart, the Garbled Circuit, can evaluate the same function, but by taking garbled input with garbled output, where only authorized user can decrypt the garbled output. Therefore, we can preserve both Alice's and Bob's data privacy, as none of them input the raw data. The next section is the proposed framework. Let's start with a traditional framework with privacy protection to illustrate the task. Suppose there are M hospitals where each has its local privacy data, such as the mortality of a subpopulation. Then each hospital may want to rank the mortality among all neighboring hospitals and compare with every mortality in a cloud environment. In case without privacy protection, all hospitals need to send their raw data to the cloud. Then the cloud could compare the data and rank each hospital. Finally, the cloud returns the results, where each hospital gets its mortality rank and the comparison with average mortality among all the hospitals. Then hospital may make necessary adjustment to improve the healthcare if it has a higher mortality than in other hospitals. However, the previous setup requires the exchange of raw data, which fails to protect data privacy. In the next, we will introduce the proposed privacy-preserving framework. In the new framework, we introduce an extra critical service provider. In the upper right. Which will cooperate with the cloud to answer the hospital queries. First, the critical service provider sends the public key to all hospitals and the cloud for homomorphic encryption. Each hospital will use the public key to encrypt its data and send the encrypted data to the cloud. Because the cloud does not have a private key, it learns nothing from encrypted data. Based on homomorphic addition and multiplication, the cloud can compute the encrypted average over all inputs. By then, the cloud has n+1 encrypted data, as in this figure. In the next step, the cloud generates n+1 random masks in the bottom. The cloud encrypts all of the random masks using the same public key. Then add each of them with corresponding encrypted data following the homomorphic addition property. The cloud will get n+1 encrypted summation of the data and the random mask. The cloud will send this encrypted item to the critical service provider. Because the critical service provider has a private key, it can encrypt all the encrypted items. However, because all of the encrypted items contain the random mask, the critical service provider cannot learn anything of the data. Given the random mask generated by the cloud and the decrypted item with additive mask from critical service provider, cloud and the critical service provider can first generate garbled inputs, which can be fed into a garbled circuit for privacy-preserving comparison. The garbled circuit will subtract the garbled random mask input from the garbled input provided by the critical service provider in a privacy-preserving manner. In other words, all the intermediate results in the garbled circuit are also garbled values. Then the garbled circuit performs comparison operations over these garbled value data to get hospital ranks and their comparison with average mortality without reviewing any raw data. Finally, the cloud will send the ranks and comparison to the corresponding hospitals, and the hospital can then use this information as reference to improve their healthcare. The next section is the experiment results. We have extracted 924 ICU death record data from the MIMIC-2 clinical dataset. This table below shows the attribute of each record. We evenly split these ICU death records among 4 hospitals for 221 records each. This table shows the comparison result under different criteria, such as the age of 20, 30s, 40s, and 15 unmarried male persons. For each for each criterion, our method securely output the ranks for each hospital. In this table, the red ranks indicate the corresponding mortality is above the average in the corresponding criteria. And this slide shows the average execution time on each key cryptographic operation over 1,000 trials. We can see that Garbled Circuit is the most time-consuming operation. Moreover, we provided the estimated execution time of the same operation that was applied on the plaintext as reference. This is the summary and filter direction. We have implemented arithmetic and comparison operation in cryptographic method based on cloud client model. In the future, we will build advanced systems such as the regression model. We will speed up the computation through parallel computing. And question, I'm ready for all questions.